that time, there is another type of regression that is called logistic regression. And this is more important and very, very basic concept for many other algorithms, like a neural network, deep learning neural network, which is extension of that is a deep learning, which is going on everywhere nowadays. So this is basically the building block of all those algorithms is a logistic regression. So if you pay attention and learn well and implement all the concept of logistic regression, um, like reasonably good, and if you are going to solve some assignment problems or some project with logistic regression, then you understand. Then you can generalize it, or you can extend it, your knowledge to other neural network, and at least you know that what's going on. And when you will when somebody is telling you that, okay, this is a sigmoid function, this is softmax, or this is what, like a that's cost function. So you will understand, okay, this is classification. So that's a classification cost function, how this work. It works similarly to logic. So this is the content we are why what is the difference between linear and logistics, and how many types of logistic regression can be, what is the binary classification, how the hypothesis will look like, and what function we have to choose, which is sigmoid, and what how cost function look like. Wow, then if we have a cost function, then we have to optimize it, and we'll be using gradient descent again. And that's it. And then how to deal with multi-class classification. I'm going to cover this for this today, and tomorrow we will same time. I'll go over those IPython notebook, and with some live data handling, and we'll cover it again. So today will be only the presentation. So logistic regression, sometimes we call it classification, and I prefer call it classification because it is what we're doing. So so and it is another again, it's a supervised learning algorithm. We are currently working with the supervising a supervised part of machine learning. And any supervising learning algorithm has a label data set. So data will, when I talking about label data set, then data will be in pair. So you have a target or output variable y, and then you have a set of corresponding predictors or your feature variables to each y. So suppose you have a y1, then you have a predictors like a what we call that, that x1, x2, x3. Then they're the subscript. Then you can put the superscript as a x1, x11, x12, x13, and x1n. And if you have a another next value of y2, then x21, x22, x23, those kind of stuff. So your data comes in pairs. So each and every label data points to have a corresponding features. So that only we can learn, because we want machine learning is basically learning from data and finding your formulas, doing and finding your basically the parameters and optimize your cost. And that's it. That's it. That is a basic machine learning step. So here we have label data set. This is from last. This is a cartoon from our last presentation, and then some of data we are going to use as a training, and then we have a learning algorithm. Either it's a logistic, linear, or CNN, or SVM, or gradient descent, or random forest, or any other. So then Then we pass the data from learning algorithms, and every learning algorithm has their own cost function. And we will use some method to minimize our cost. And by minimizing our cost, we will be able to learn those unknowns, those betas, those parameters. And by the end of training, that part we call the model training. By the end of training, and we have some good mathematical formula, and then we'll give any features, any features like x1, x2, x3, and then our model able to tell that, okay, you show me the picture of boat, and the probability of boat will be high. So for the logistic regression, for if we have the many class we have, that many output is possible, and each output will be assigned to a probability between 0 and 1, and then the higher the probability, the class will be the our output, uh, like our prediction. So the difference between linear and logistic regression, uh, first is that linear regression is a continuous value output, and logistic is a discrete, like 0, 1, 2, 3. So both are regressions, but one is uh, continuous and another is discrete. So example of your continuous valued output, like a price of house by the size of house, and we can fit a line, and we can tell at any points in between those 2 points we can find any house which is if this is 3 bedroom, this is 8 bedroom, then what will be the price of 6 bedroom? Then we can, or size in a large size. So then we can see, oh, okay, it will be somewhere in between here and this is, then it will be this price in dollars. So you can basically project uh, and find about what will be the price of any continuous value between this and beyond that. If we have a line, because line can go both direction, of course there will be no negative value if we are thinking that the line will be go beyond, but a line can be go in that direction, and you can find a price of more bigger house that will be continuous. And in terms of logistic, you have a given class, and then you have to assign that class to any of those outputs. So when you are showing uh, dog here, and it should be a probability of dog will be highest, and probability of other two classes will be 0. So that is a prediction. And if you're showing some like a house here, and your machine will try to understand out of those three, try to understand that house in terms of what that your machine had already seen, like the pictures of a bird, dog, and cat, and that is that house is going to assign to any of those classes. That will be really long wrong. So that's how you choose your data. Mm, mm. Um, that is depend upon how you choose your data. You have to be careful that you are training your model to and you are predicting the same on those you have trained your models. You cannot predict uh, the value for that your model is not trained for. That's what the learning comes from. Model, that is a kind of limitation. That is the difference between our human and machines. We can make a decision. Even we cannot make a decision what we have not seen, because we also learn with experience, and every experience is is kind of looking at data, training our models each and every time from our birth to till now. We have our experience registered, stored, and we have optimized our algorithm. We have our mind has our neurons has their betas, and whenever they see data, and but our mind is a very like a pretty general algorithm. So because it is trained over vast amount of data. Now there is another breakthrough just come up in a GPT, and they trained the NLP model on like a billions of like data points, or billions of variable. And so that algorithm is pretty general, so that how bigger or how bigger data set is seen by your algorithm, and richer the experience, and more better the decision you make. So that is basically out of point, but the point I want to make that first, you have like you train your model as big as data set you have, and another things, you do not try to predict from your model that your model haven't seen yet. So so for continuous, we have seen this that right side the left side graph, and this we can see that the data house and price has a linear relationship, and we can fit a line, and this is a continuous value output. For logistic regression, in a in a in our variable space, they may have some clusters, they may have some decision boundaries, they have they will be discretely distributed in this variable space. So that is another difference. So how the training data look like? This is your target variable. You are predicting price, and this is your area. You can see that this kind of continuous, and your training data for your three class three feature variable look like this, and then your target variable will be a class 0, 1, 2. So type of logistic regression, basically two is one is binary. When you are when it's binary, it's two values only, 0 and 1. And when there is more than one classes, that is multi-class classification. Maybe you have more than one class at a time, like 0, 1, 2, 3, 4. And if you have a five classes, and sometimes you may have more than five classes. Uh, and that if you have multi-class problem, that will be your multi-class classification. In binary, you have two output classes. Y is always will be 0 and 1. Y is your target variable. And in the practical problems, it can be email, either it's spam or not spam. And how we decide this email is spam or not spam, that is called our predictor, our feature variables, by looking domain name, subject, email address, content, and etc. So when somebody think about this problem like spam and not spam, that's a very hard problem to solve. You all of you have experience. Sometimes you are still with this much richer data sets, and this much of progress in a machine learning, you can still find your good emails into spam folders, and sometimes your spam emails into your inbox. So uh, their models are not perfect. Models are try to model like the process, but like there is saying that no model is perfect, but some models are workable. So we can got us some models that can work for us, but no model is perfect. So when we think about the problem of email spam or not spam, then somebody um, someday start looking at emails and then say, okay, what is the common characteristics of that emails are spam? So they try, okay, these are the 4 or 5 features we should look, and that 5 features will tell us is email it's being spam or not. Is domain name is something suspicious? Is subject is suspicious? Is email address is suspicious? So then some algorithm try to look at the content. Is it look like it's spam? So all these are our features, and then somebody has to have built data before thinking about solving this problem. So now, if we want to solve the problem of spam not spam, we will find somewhere data, and we will and then data will have like already somebody decided like this mail is spam because of this. These are the your features. This mail is not spam because these features are this that. So they have very good label data set, and they each of then they uh, provide like try to learn what those parameters. Try They decide to go with logistic regression because the binary classification or some advanced type of classification methods nowadays, maybe deep learning, and then they have to have learned their parameters. And when they have learned the parameters, somebody learned the parameters, that is your your formula, your hypothesis is ready, and now you can pass the data. And whenever your email come to your client, you just before sending into any folder, spam or inbox, or any, maybe nowadays there are some other folders like I think Gmail is giving some other folders like a social or something. I forgot. There are 2 3 names, and then Gmail will send those uh, email into respective folders. Nowadays, this email classification is a multi-class classification because by looking at the emails, your algorithm is going to decide which folder should be placed, and if there is a 5 or 6 folders, then it will be a six. Then it will be a multi-class classification. Oh, okay. Anytime you can ask the question uh, if you want. You can interrupt me anytime.
Sir,
So yeah,
sir, can we say that
go
in
on.
logistic regression, the data is partially distributed?
Wh- What can you repeat your question?
So can we say that in logistic regression, the data is partially distributed?
No, partially, like these words are not right. Partially and distribute. So your data will be like find like in a phase space or in your variable space, data will be separated by the well-defined boundaries. And
Okay.
if your data is separated by boundaries, then if you can, now say this is data of dog and cats, and if you can draw a line in between them, and if you know, and that will be our boundary. So in a logistic regression, we want to learn that boundary. If we know the equation of that line that can divide these two spaces, um, uh, no, so then we can see that, okay, this side of this line will be cat and this side of this line will be dog.
Okay,
So
sir.
so that's yeah. But I got your point. You want to say that data will be in the corners away from each other. Each class will be in a small confined space in
Yes, sir.
in a variable space. Yeah. So if we plot x1 and x2, we can see that the data will be far from each other, not First, it will be not a linear. If this kind of clusters will be look like, then you can train cluster algorithm. You can do the logistic regression type of, like, you can try SVM. Those classification algorithm will work here. And
Okay.
if we plot x1 and y, because every x1 y will be 0 or 1, so we can find that they will be at the either will be 0 or 1. So so this kind of how to frame mathematically this kind of problem classification, that will going to cover next. So let's say you have uh, tumor size data, and you want to predict that tumor is malignant or not. So on the basis of size, if the tumor size is bigger than certain size, it, tumor may or may be malignant. Before deciding that those about whether the tumor is malignant or not, we need data. So let's say we have some data points. So how we can learn this? How we'll come up with a model so that we will pass the tumor size every time it will tell us tumor is malignant or not. So first approach, we can fit a line. But last time we talked about that there are linear regression assumptions, so that data is not linearly the data doesn't have a linear relationship. The data doesn't have a look like there is no linear relationship look like between two variables, like feature variables and target variables. If there is no correlation, then you cannot fit a linear regression. But let's say we fit it, we want to predict it. And for any tumor size, we will be getting a value, something value for we we have this equation of this line. We will then we have a y is equal to mx, and or y is equal to beta 0 plus beta 1 x. And then we have beta 1, beta 2, and we have a certain tumor size x, and then there we will be getting a value between 0 and 1. And let's say we got because this is a linear regression, we will getting a continuous value. And let's say if this value is above zero point 0.5, we'll say it is tumor is malignant, and if it is below zero point 0.5, then tumor is um, a non-malignant. And if we think by looking at this, I think this is our decision boundary. And then if the tumor size is that this side of the bigger than a certain size, then it's only malignant. So this linear line can tell us very well here. But suppose we have another data point, and we want to include this into the line, and we fit another line. So now our decision boundary will come here, because at this x we are getting zero point 0.5. X greater than this will be we are getting if we x is like our tumor size is greater than this size, then only we are getting the value of our target value, a variable greater than zero point 0.5, or then only our we can say that a tumor will be malignant or not. See, now these two data points, still we are predicting it right. Those are malignant. But now these two data points, we are not going to the other side of the boundary, and then it's though it's malignant, but our model is predicting it's non-malignant. And this is a life-threatening things. You cannot do this in this kind of problems. Be very careful. So so to this kind of problems, what how to solve? Like, we know that um, we have to predict our target variable either 0 or 1. Yes, yes or no, malignant or non-malignant. and that our hypothesis, our formula should return us a value between 0 and 1. And keeping that in mind, uh, we use sigmoid function. This is called logistic function. So we are applying transformation here. So we transform our data into a different space, a logistic log space basically. So our hypothesis will be h theta x will be g, the theta 1 plus theta 0 plus theta 1 x will now become g theta, or this can be written as this theta 1 theta 0 plus theta 1 x we can write as a theta transpose x. Okay. And this function has a like characteristics. This always gz is always will be between 0 and 1. So 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 we use sigmoid function to transform our h theta x will be uh, this h theta x will be 1 by e to power, we will replace g as theta x. So because theta transpose x, we are replacing this z with theta transpose x. This will be our hypothesis, and this hypothesis, our h theta x, what we want, will be in the range of 0 and 1 now. And it has parameters as many as class we have. We have two classes, and then and no, if we have two feature variable, then we have then we'll have three thetas, theta 0, theta 1, and theta 2. If we have one feature variables, this theta 0 is our bias unit basically. So we have to find this theta 0 and theta 1 that is unknown. When we have those theta 0 and theta 1, for then we can predict for every given x, every given feature variables. We will have some output, and then we can compare with y. So this is a sigmoid function, and this is look like this. When h theta x when x is small, then it will be sigmoid function will be 0, and when x will be very very big, it will be going to 1. So now we have our oh man, our hypothesis, and we want to optimize our thetas. We want to find our thetas, and then we have to have one cost function, and we have to optimize that cost function for those parameter of ours, theta 0 and theta 1. Last time we saw this was our cost function, like our cost function was like this. And like we don't know yet what will be our formula of our cost function, but let's say for now we will write it as a cost, and that we know that cost function will be the function of our h theta x, and like that is our predicted y, and that is our actual y at any, and for the any ith sample. So, and for then we will do it for all the samples, and then sum the cost over all the samples, and then we'll see what the cost we are paying for that prediction. But if we are using this theta 0 and theta 1, if the cost is very high, then we'll try to minimize it, and we will keep minimizing it till we find the lowest cost. So the cost function, um, the one property of our cost function should be convex. Um, so for for the convexity, uh, uh, for the logistic regression, we use log of our hypothesis as a cost function. So log of h theta x. There is no involvement of y yet. So so if y is 1, then we'll use this one, and if y is equal to 0, then we will use this one. So because log 0 is undefined and log 1 is equal to 0. So if this we want to predict 1 and our h theta is 1, so then we our cost should be 0. And if we want to predict 0, our h theta is 0, then log 1 is provide us 0. Because this will be 0 and we are predicting right, then there is no cost. And if suppose our y is 0, and if we are predicting h theta is if our y is 1, then we are predicting your h theta is 0, then our cost will be very, very high. So like log 0 is even not defined. So if we use this one, uh, like cost function, uh, uh, by applying the log to this cost function is gives us make this cost function more convex. If we use non-log without log, we can optimize without log. Without log, this function will have many local maxima. And once our solution comes to one of those maxima, it will not come out of this. There are ways you can find a global minima in the middle of local minimas, but but it is then we have to take some different measures. But it is if we use the log instead of h theta x and use log of h theta x, then our function will be convex. So like this. So so this will be our cost function, and value of this one will be log h theta x if y is equal to 1, because and I why this y only have two values, 1 or 0. If this is 1, then we'll use this one as a cost function. If y is equal to 0, we will use this as a cost function. Why? Because log 0 is very, very high. So when this um, when we have output, we have actual value of y is 1, and we are predicting h theta is 0, then our cost will be very high. So this top functions will be plotted like this. And if our y is equal to 0 and we have actual y is 0 and we are predicting by h theta x h theta x is 1, then 1 minus 1 will be 0, and then this will be very high cost. And opposite of that, if we have y is equal to 0 and we predicted y is equal to 0 by h theta x is equal to 0, then log 1 will be 0. So these two lines will give us kind of a convex, and it is easy, it is feasible to find a global minima of this convex function. So that's why a cost function is designed to this. So this is our cost function. This is our formula, and this is our cost function. This has two value. When is 1, we have to use this. When is 0, we have to use this. And from this line, after some manipulation, we can write this like if y is equal to y log of h theta x plus, like this minus we can take out. Just we will multiply y here and plus 1 minus y here. Now see, if your y is 0, then this this part of the equation will become 0 and only this will work. And if your y is 1, then this 1 minus 1, this term will become 0 and this will be there. So this is another way to writing this. So we can write cost as a function of h theta x and y as this one, and we can replace this by this. And now this will become our j theta. This is our cost function. So the cost function of linear regression was different, and cost function for the logistic regression is different. And and there are many other types of cost functions in depend upon your algorithms. So now we have our hypothesis, we have our cost function, and now we have to find thetas. So now we have to optimize. How we optimize? We know that our cost function is convex. So now we'll start the process of minimizing, and we will use gradient descent. Similar gradient descent we have used. So we will start our algorithm taking any thetas, and then we will multiply, we will choose some alpha, we will find the gradient of each theta, and we will update theta. Till then, we will keep minimizing it. And so the derivative in the last linear regression was this. We know our h theta, we know our y, we know our x. We will put all those values here. So that will be our logistic regression. And for binary logistic regression, and I will go over it again tomorrow. By that time, you may read from our maybe website. There something will be there to read, or maybe you can follow book and ask Lapreet or Saurabh to for a reference book or notes. And it's very important that you read some standard reference, so you will be more open. And just so this is standard steps. Like you have your hypothesis, you have to have designed your cost function, then your goal is always same, to cost minimize your cost for your given and find your thetas. And then you can use any method to minimize it, and most of the time we are using gradient descent. And in a computer science, it's a very reliable way. And then this is how we calculate the derivative, and we will put that derivative here, and we'll keep repeating like you did in linear regression. So how to deal with uh, more than two classes? So your target variable will be always will be more than one, like 0, 1, 2. If you have three classes, if you have four classes, 0, 1, 0 to 3. So how to deal with the how this is just a trick. It's no new other method. The logistic regression is complete. That was your formulation, that was your the steps you have to keep in mind. But multi-class classification from binary classification is just a trick. So let's say you want to predict weather by looking at the weather variables, like how much humidity, sunny or not, or those like how much other by looking at the weather variable, how is the wind, how is cloud, and mm, how much humidity outside, and how sun is covered, what is the time, and those may be your features. And you want to predict is outside will be sunny, cloudy, rain or snow, and maybe the time of your one feature. So now you have four classes. If you are have a medic you are a doctor and doing medical diagrams, then you want to tell this person with have a like COVID or not COVID, or is ill or cold or flu or something. Then you have three classes, and then the cross triangle scare you if you want to identify the shape. And then you have another multi-class classification problem example. So let's say you have three like a shape classification, and in a grid space, they are uh, concentrated in in a different areas, and then you can decide if you want to predict for a given set of feature variables, whether it will be a cross, uh, rectangle, or triangle. So what you will do, you will first we want to predict this class, and we will make other two classes, club other two classes into one. So basically, we are solving binary classification. We will apply binary classification to this, and then we will apply binary classification to this, and then we will apply binary classification to this one. So then, for a given set of feature variables, every class will return you a probability, and then you choose. If suppose you are on the basis of your feature variables, your shape is rectangle, so probability of this class will be assigned to this one, and probability of this class will be minimum, small value, between 0 and 1, and mostly below zero point 0.5. And you know yet that your feature variable, on the basis of feature variable, your class should be in a rectangle. Then you are if you are predicting the triangle, then the probability of being that on the basis of that feature variable, probability of that class being a triangle will be very very low, maybe zero point 0.3. Maybe this is zero point 0.2, this is zero point 0.3. And then the probability of uh, of that class is being rectangle, maybe zero point 0.5 or point yeah, we have to conserve the probability, maybe the zero point 0.5. And then this is zero point 0.5, this is zero point 0.2, this is zero point 0.3. And now you have to this is your boundaries, and this is positive class, this is negative class, by solving like a binary classification. And now this is our boundaries. And then you have to this like now you this class has a mm, zero point 0.2, this is zero point 0.3, and this is zero point 0.5. Then when you are making a decision, just do the maximum of all the probability, all the classes, and then your output will be assigned to the class that is finding the maximum probabilities. So that is the trick we used when there is a multi-class classification. So this a pure binary classification is used here, and just like if you have three classes, we did it three times basically. If we have four classes, we'll do it four times, and then we will keep the probability of the class which have a maximum probability. So that is our logistic regression. So now I will cover uh, go over our IPI and B tomorrow same time, and that by the time you will read, and I will say just try to read one standard reference, or go through our website content and come up with questions tomorrow. Like make sure you understand the concept, and by reading yourself, give some time, like hour or two or three, sit down and read it carefully and try to understand. And if not, then note down your questions, ask your question tomorrow, and we will start from there. Okay, guys, if you have any question for me, let me know.